let's jump into first one and the performance demo. So within this demo, I would like to show you the WBA6 system architecture in a bit simplified way, and then switch into the project itself. And the main impact is to demonstrate that running the Bluetooth low energy on WBA6 has a very minor impact on the overall system performance, and still there is plenty of performance for your task needs, computation, whatever to put into the microcontroller. And last, there will be also look into the priorities in the system and the flexibility WBA6 is offering. For the architecture, as you can see on the simplified bus matrix, you can see that there is the Cortex M33 through the cache connected to the bus layers as is flash, RAM, or peripherals. But the peripherals can be served not only by the Cortex itself, but also by the GPDMA. So right now, with the options for the linked list, you are able to do quite complex tasks without any CPU influence, and therefore spare the CPU performance for some other task. So how to demonstrate the performance that there is still plenty remaining for you? We took the chance that already we have on the EMBC. So here you have the link, review the score of STM32WBA6 with the same core and same frequency. The same shall be achieved on WBA6 as well, as the score is a little bit older. Now with up-to-date IR version 9.69.4, I was able to achieve the score of 413.9. Additionally to that, I took the repository BLE heart rate example and merged it with hotspot example for core mark calculation. And thanks to the FreeRTOS capabilities, I am able to monitor the time which I spent in various tasks and also get the GPIO signalization on switching of the task, so I can see what is running at the given time and what is the overall consumption. So right now in the project which I will show you, the highest priority among the system is for the radio to achieve the best radio performance. Then a random number generator is used. Again, this is the heart rate sensor application. So there is the task for simulation of the data, one additional task for the statistic, and the very lowest just on top of idle is the task which is calculating the core mark. So let me jump out of the presentation. And so now, as mentioned, the project is in IR, already loaded. And for support, I have here the serial terminal. So let me clean it. And okay, so I will need to refresh. Probably I forgot from the previous one. So this one. Additionally, I have the logic analyzer to observe the performance. So that I will start a little bit later. And there is also the Python script for visualization of the task. So let me run on the screen as well. So a little bit waiting for the IR. Now it should be jumping into the debug. So I don't need to debug right now. And okay, I can see that the application is running, and now I spend the majority of time in idle task. So by the button press, I can start the advertising. So to have there at least some load in the application, so the radio random number generator tasks are running. And if again by the button press, I start the core mark calculation, I can see that right now, majority of the time I spent in the core mark task, while from the GPIO signalization, it would look that radio and random number generator tasks are quite dense, and there is not so much time remaining for the core mark calculation itself, but still I can achieve quite a good result compared to previous one when I'm advertising on maximum frequency. Again, I can also connect the phone. So I have here the mirrored screen. So I will connect. I can see here the negotiation of the connection interval and supervision timeout. On button 3, I can change to different connection intervals. So right now I'm on 50 millisecond, which is still quite fast, and activate the heart rate service. So now the speed for the update of the data is faster. And again, with this, I will run the core mark application. So here I have summarized for you the result which I am able to observe on my site. So without any RTOS, any overhead, I get the core mark result of 413.9. Just by adding the RTOS, so some free RTOS overhead, I decrease by 1%. And then what we consider as typical cases, still quite aggressive for the timing, not very low power setup with 100 millisecond advertising. We are on 98.2% of performance with 50 millisecond connection interval and enabled notification, while in background are still calculated the data for the heart rate. We are still on 97%.
Lubosh,
Yes.
can you go back to your result?
Yes, sure.
So all this is based on IR.
Yes. So
Now,
yes,
but
this is
it reproducible as well with other compiler?
partially. So here this is on IR with maximum optimization targeted for speed, and tested also with Kyle, where I am able to achieve a little bit decrease performance, but still pretty high. So there I'm running at 403 without any RTOS. But with GCC, I can observe that the performance drop is already a bit more significant. So there is some justification why this compiler are paid. But yes, you can still run with this and achieve some reasonable result. One more stuff I wanted to show is that it's quite usual that within the RF system with single core, it's mentioned that RF need to be the top priority in the system, top interrupt to work correctly. Also, we have in our recommendation that RF need to be the highest priority among the system to run correctly. That's still the same. But also here, we can introduce some higher priority task, which is blocking the RF. Yes, the RF performance will decrease, but the link is kept if the time is below the supervision timeout. So which is like 4 seconds usually. So you have big flexibility to run other important stuff in your system. So you say ADC is more important for me than RF. No problem here. Still, you will be able to sustain the link. User won't get any decrease of experience, and you can run on your side. Within the project, this is prepared with in up3rtos.c that I will add here one high priority task I'm showing you because you will be later on able to download on your site. It's already on STM32 hotspot and try yourself. So here the high priority task is above the RF or any other custom task here. And in the task, I'm periodically disabling the RF interrupt and then introducing the blocking wait. After that, I will again enable the interrupt and let the system to reschedule to other task. So here on my side, I will add one more channel to show also that there is a high priority task. So let it run. Okay, and it will take a while before the IR will let it run. So I can see that the high priority task is now running. By the button press, I will start the advertising. So again, I can connect from my phone, start the heart rate, and also start the core mark calculation. So you can see the data are still running, even though during this high priority task, nothing else can be executed. And here it's 52 milliseconds. As mentioned, I could go up to 5,000 milliseconds. So there is enough time for your high priority task execution. For sure, the core mark results have decreased quite significantly now, but this is not the purpose right now. So let me go to the takeaway, to the wrap up, what I wanted to show. So still with the convenient architecture of WBA6, for typical Bluetooth application, we are below 3% of performance taken by the RF. Still a lot of time spent in idle, prepared for any task in your application. Possible also to add additional task which will be autonomous thanks to autonomous peripheral. And we are not forcing you to have the fixed priorities in the system targeting just the RF. If something else is the priority, try it or use it as you need. And as already a little bit introduced, the example is already on the hotspot. If you are in favor, please try. We'll be glad for any feedback and discussion about that. So thank you for now. And now let's check how the WBA6 is performing regarding the low power. So opposite side of the spectrum. Dominic, stage is yours.